understand what you're looking at with a mathematically precise definition. Like this NBA example of all the NBA players got confusing quickly. So one of the things we want to do is attend to precision. The next thing we want to talk about, which you've seen before, but you may not have seen in this way, I don't know, is functions. So I'm going to give you the precise definition of a function. No, I'm going to give you a precise definition of a function. So a function in mathematical ideas consists of three things. You have to have a domain, which is the set of anything you could plug into that function. You have a codomain, which is the set of all things that you would accept as an output of that function. And the third thing is you have to have a rule that tells you each element of the domain, what element of the codomain it should map to. So the way we do this, when we do this mathematically, well, there are different ways to do it. One way that you will see is this pattern called something like this. You have the symbol for the function, you have the domain going to the codomain, and then you have what it looks like when you actually map to an element. This is one way to express a function. So can someone give me an example of what a function that you know that's a familiar example that might fit this pattern? X squared, if we said f from the real numbers to the real numbers, x maps to x squared. This would be a perfectly valid description of a function. This is a highly symbolic way. Awesome when you have these symbolic operators. Something that you really need to wrestle with is the fact that human beings make up functions, and someday you will make up functions. So let's think about sine. From the real numbers, the interval -1, 1. X maps to what? Well, it's like a recursive definition. It's what everyone was going to say. So now I've gotten it out of the way. X maps to, I can't say sine of x because I'm trying to define sine. You have to have a very verbose description because that's what this actually is. The y-coordinate of a particle traveling the unit circle when the ray from the origin to the particle makes an angle of x, and this is why theta would have been a better choice here. Makes an angle of theta with the x-axis. That's the definition of sine. When you say sine of x, you're assuming that you know how to calculate that you know what that is. That's like 300 years of mathematical challenges, going from this description to how to actually get a number. So functions are not formulas necessarily. Functions can be formulas, or functions can be expressed through formulas, but they're not always formulas, and they're not always best understood as formulas. And if you have a function for a formula, it's probably because, if you have a formula for a function, it's probably because someone at some point came along and said, I'm defining this, and here's the formula. And now we have a name for it, and we can start using that formula. But functions are rules, and you can have a function defined on a finite set, just like you can have a function defined on an infinite set. So what if I said the function from 0, 1, 2 to 0, 1, I need to stop using f. This is the last time I'm going to use f. What if I said f of 0 equals 1, f of 1 equals 0, f of 2 equals 0. Is this a valid function? And this, if you have a finite set, then you can just list all the values. So now here's my challenge to you. And I'm going to give you a few minutes to think about this, and then we'll come back and discuss it. How many different functions are there from the set 0, 1, 2 to the set 0, 1? Do you understand the challenge? How many different functions are there from the set 0, 1, 2 to 0, 1?